We've now taken a look at the function of the skeletal system. We've also looked at the different regions, the axial and the appendicular skeleton. And we looked at the different shapes of bones within the skeleton, focusing on the long bones. So now we want to look at how bones actually develop in the first place. And so we have this image here showing an analogy of two different types of cells that are involved in bone formation and bone development and bone growth over our life. The two types of cells are osteoblasts, which build bone matrix, and osteoclasts, which break down bone matrix. So they're represented in this analogous image here by somebody who's building a wall, so representing the osteoblasts that build bone matrix by taking calcium, depositing it into the hard matrix that is surrounding the osteocytes within the lacunae, as we saw in the long bone. And then osteoclasts, shown or represented by the image on the left of the person breaking down the wall using a tool. The osteoclasts break down the hard bone matrix and release the calcium from it into the blood. And so what we can do then is differentiate between the intramembranous and endochondral ossification by starting off from an offspring, from a fetus. And what happens is most of the bones of our body undergo ossification from cartilage, as is shown in blue here. So many bones of our skull, our spine, rib cage, and our appendicular skeleton, what happens is they all start off as cartilage when we're a fetus. So when we're actually first developing in our mother's womb, we actually don't have any bone. We're very flexible cartilage, and those form a sort of blueprint of our skeletal system. The major bones in our cranium, in our skull, undergo ossification by taking connective tissue and undergoing intramembranous ossification. The ossification from the cartilage is endochondral ossification, and we will take a look at that in just a moment. So when I'm still a fetus within the womb, we actually don't have fully formed skull bones. And so what we're showing in the image here is that the skull itself undergoes intramembranous ossification by taking the connective tissue layout of our skull and replacing that connective tissue with bone, forming the flat bones of our skull. But what happens is not all of that connective tissue is actually replaced by bone before birth. And so we can see labeled here the anterior fontanelle, anterolateral fontanelle, posterolateral fontanelle. Sounds like mouthfuls, but really anterior just means at the front. Anterolateral means at the front and sides. And posterolateral is referring to at the back and the sides. But these are areas of connective tissue that do not form into bone so that the skull is flexible so the offspring can be birthed by the mother. And so as the offspring is being birthed, the skull bones sort of push together in those fontanelles, and then after the child is birthed, the skull bones go back to their original position, and then the fontanelles end up undergoing more intramembranous ossification, where those that connective tissue is replaced via osteoblasts and shaped via osteoblast and osteoclast function, as we were mentioning in the previous slides. So again, here's just another image of an offspring where there's a lot of bones, but there's a lot of cartilage going on because, again, first there was a blueprint of cartilage that was then over time replaced by bone due to the function of the osteoblast building bone and osteoclast breaking down some of the bone and the cartilage and reshaping the shape of the bones. We want to take the time to go through the steps of endochondral ossification, because it's a little bit more complex than the intramembranous ossification, where we say the bones of the skull are first connective tissue and then just replaced over time by bone tissue. For endochondral ossification, what we have is the blueprint of cartilage, and so before we even get to the image shown here on the left, we would have a full blueprint of cartilaginous bones. They're not really bones, but a cartilaginous blueprint early on in the development of the offspring. What happens as the offspring develops is that blood vessels come into the periosteum, bringing in calcium and providing nutrients to osteoblasts that then build what is called the bony collar. You can see it in the image here just forming around the diaphysis of the long bone. And so the bony collar is just like what it sounds like. A collar wraps around your neck for your shirt. A bone collar wraps around the diaphysis just on the outside, and it is made up of bone, but there is cartilage on either side of that bony collar, as well as inside the cartilage that is starting to become calcified. What happens then is we start to form what's called the primary ossification center. So the blood vessel continues to bring in calcium as well as other nutrients, and the osteoblasts start to develop more and more bone. Osteoclasts at this point will break down some of the bone in order to help shape it, but the osteoblasts are producing a lot more bone, and what we notice here is that the bone starts to get wider and longer. At the end, towards the cartilage, the osteoclasts are chewing up the cartilage, breaking it down so that the osteoblasts can actually build bone in replacement of the space where the cartilage was found. Over time, as this continues to develop, we have what's called the secondary ossification center. And so up at the top, you can see that there's a second point in the epiphysis where cartilage starts to be converted into bone. Again, it's the same process. Osteoclasts are starting to break down the cartilage, and osteoblasts are starting to build bone. And so here we have, over time, a larger and larger secondary ossification center, and we have a larger and larger diaphysis and medullary cavity starting to form, and we're reducing the amount of cartilage that is found within the bone. The bone is getting both thicker as it develops and longer. As this process continues, we end up at this point where we have a quite developed secondary and primary ossification centers, and there's very little cartilage left. What you'll notice is that there's cartilage found in the epiphyseal plate. Earlier on, when we looked at the long bone, we talked about the epiphyseal disc. And so the epiphyseal plate will develop into the epiphyseal disc, but for right now, while the bone is still developing, the epiphyseal plate is where there is still cartilage. There are still cartilage cells that are developing more and more cartilage matrix, but what's happening on either side of that epiphyseal plate is osteoclasts are chewing up or breaking down the cartilage, and osteoblasts are continuing to build new bone. And so what happens over time here is that the bone gets longer and longer. And so this is when a child is getting taller and taller as they develop. Eventually what happens is around the age of 13 to 16, as the bone gets longer and the bone gets wider and continues to develop, the epiphyseal plate starts to slow down in terms of the amount of cartilaginous growth. And the osteoblasts and osteoclasts kind of catch up, if you will, and get rid of all of the cartilage that was there. And so we can see in image G here the epiphyseal line, as we mentioned earlier in the long bone discussion, where it is no longer cartilage, but the cartilage has been completely replaced by bone. In order to discuss this next learning outcome, discuss the hormonal control of blood calcium levels, we need to make a connection among the last few portions of the skeletal system. And so we'll get here into hormones and how they control blood calcium levels, but we also need to remember that osteoblasts build bone by taking calcium out of the blood and building new bone, so placing the calcium in the matrix. The osteoclasts break down bone, releasing calcium from the matrix of the bone into the blood. Therefore, the osteoblasts reduce the blood calcium levels, and the osteoclasts increase blood calcium levels. What hormones function to help regulate this? So here we have the body, and we can zoom in on the neck region on a specific gland here. So this is the thyroid gland. And then embedded in the thyroid gland, there are 4 regions that you can see here that are the parathyroid gland. And these are the 2 glands that provide the hormones that control the blood calcium levels. So let's take a look at the parathyroid gland first. The parathyroid gland and the thyroid gland both monitor the blood to measure how much calcium is in the blood. The parathyroid gland's function, however, is to monitor and know that when there's low blood calcium, that they need to release their hormone, which is called the parathyroid hormone, into the blood. The parathyroid hormone will go into the blood under the low blood calcium conditions and go to the bone. When it arrives at the bone, it will stimulate the osteoclasts to break up bone, so break up the bony matrix and release the calcium from the matrix into the blood, thereby increasing the blood calcium levels. And so the parathyroid gland, again, monitors low blood calcium, releases the parathyroid hormone that stimulates osteoclast activity in the bone that causes an increase in blood calcium levels. That increase in blood calcium levels goes back to the parathyroid through the blood. The parathyroid is monitoring the blood and says, okay, the blood calcium levels are now increased. I can stop releasing parathyroid hormone. The thyroid does the opposite. It monitors high blood calcium levels, so it's monitoring the blood. If the blood calcium levels get too high, it will release its hormone, which is calcitonin. Calcitonin will go into the blood, go to the bones, and they will increase osteoblast activity. The osteoblast will take calcium out of the blood and put it into the matrix, will create new bone matrix, thereby decreasing the blood calcium levels. Again, the thyroid and parathyroid are monitoring the blood, so as the blood calcium levels decrease, the thyroid will stop releasing calcitonin as the levels are in the normal range. We'll get into the hormonal system later when we get into the endocrine system, so that's a whole other system later on in the course. But here we start to get into understanding homeostasis and the role that hormones play in homeostasis. But we can see here that we also have negative feedback systems. We've mentioned those earlier in the course, and so it's important to note here that the parathyroid and thyroid hormones are part of a negative feedback system, where in the case of thyroid, as is shown here, we have high blood calcium levels, calcitonin is released, which causes the osteoblast to build new bone, therefore decreasing the calcium levels back into the homeostatic range.